All right, so this section is on the method of substitution or change of variables. So usually what we do is just call this a u-substitution. Now, I really don't know too much about the history of why it ended up being called u, but it is usually just u is the letter that is used for the substitution. So you can see it here, U, 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 U. All right, so what you do is actually you rewrite the integral as the function of some other function times the derivative of the inside function dx, or if you remember, this is called the differential. All right, so that's called the differential. So that's why we actually talked about differentials again, just so that you could actually go back and find the original uh, the original function and the antiderivative, and just sort of see that connection here. All right, so here is an example here. So we'll follow these steps that are described up there fairly loosely, but here we go. Identify f of x, g of x, and g prime of x to rewrite each integrand as f of g of x times g prime of x dx. So remember, we want the f to be an outside function and the g to be an inside function. So what I see here is that we have a function here that's inside of another function. So the outside function would be something to the third power right here. So I'm going to let the f of x be the x to the third power, and then I will let the g of x be the inside function. So the g of x will be 2x squared plus 1. And then I need to figure out what g prime of x is. So g prime of x is 4x. So then I can see here that if I make the substitutions correctly, that this integral right here just becomes the integral of, so the g of x, I'm going to just actually just rewrite this so that it's f of g of x times, and that would be g prime of x dx. Now, that notation gets a little bit, how do I put this, a little bit crazy at times, right? And so what people usually do then is that they rewrite the g of x as just u. So u is 2x squared plus 1, and then du dx would be 4x. But then I actually can just rewrite it in differential form to get du is 4x dx. And then if I write it using this notation instead of the f of x and the g of x, then, all right, if I use this notation instead of this notation over here, then I can rewrite the integral as just being that, since 2x squared plus 1 was u, that was u, then this is just u to the third power, and then 4x dx, if you look here, 4x dx was just du. And so this is just a different way to write this so that you don't have to deal with the f and the g of x's and the derivative and all of that. Now, the one thing that I want to point out is that you can't mix the x's and the u's together. So if you use this format, you see these are all x's. If you use this format, you see these are all u's. So I'm never going to mix the x's and the u's together. I'm either going to have all x's or change to all u's. All right, so now let's see. Let's go ahead and try another one here. So this is again just identifying the u here. So what I have here is the integral of the x squared times the square root of x to the third plus 1 dx. So I see an outside function here that is something being square rooted. So the inside function is the x to the third plus 1. So that is the inside function. So now I will just let the f of x be the square root of x. The g of x is the x to the third plus 1. And then the g prime of x is 3x squared dx. All right, so now what do you know or notice that is going on here? I can actually look at this and I see that in my problem here I have x squared dx, but here I have 3x squared dx, right? So I what was the answer for the first one? The the answer was to, well, the answer was to identify the f of x, g of x, and g prime of x. So actually, this box here is the answer where I identified the f of x, the g of x, and the g prime of x. All right, so yes, so that's what the answer is supposed to be, just figuring out what the f of x and the g of x and the g prime of x is, so that when I substitute everything in, I have this format of f of g of x times g prime of x times dx. So here I am doing that again. So I I I think that this one is a little bit different here, though, because if you notice, I have x squared in the dx here, but here g prime of x was 3x squared. So what I actually need to do is make sure that I account for every x in the integrand and every constant in the integrand. So what I'm actually going to do is I'm going to divide by 3, so, or multiply by a third, so it's 1/3 g prime of x is 3x squared dx. Sorry, over 3, yeah. So then that just becomes x squared dx over here. All right, so now what I have then is the the square root of x cubed plus 1 then is f of g of x, and then the x squared dx was actually equal to, in this case, 1/3 g prime of x. All right, and then dx. So try to just see that we had to end up having a 1/3 here that we didn't have in the problem before. So this would be the answer for this one, identifying the f of x, the g of x, and the g prime of x. Whoop. So again, I want to point out how later on we will be converting these to u's. So u would be x to the third plus 1, and du is going to, so this is du dx, it's 3x squared, so du is 3x squared dx. So then I'll rewrite this as divide by 3, so 1/3 du is x squared dx. So if I use the u format instead of the x's, then if I go with the u format rather than the x's, I have integral of All right, square root of u times 1/3 du. Or I can bring the 1/3 in front, so that's 1/3 integral of square root of u du. So again, I want to make sure that you're clear on the fact that if I use x's, I have to stay with all x's. If I have u's, I have to stay with all u's. But these really are saying the same thing. All right, let's try again, because this one is a little bit more, I don't want to say difficult or anything, but just a little bit different than the other one. So I actually have the 2x here in parentheses. So the the 1/3, see how, all right, so see how this part that I circled here does not have a 3 in front of it, right? So if I know that the derivative has to be 3x squared, so think about it like this, all right? So if my original problem is let's just, I'm gonna write it as square root of x to the third plus 1 times x squared dx, right? But remember, I want this part right here to be the g prime of x dx, all right? But if you look at what is going on here, right? If you want this to be the, well, actually, this is like dy actually at that point, since I rewrote it as in differential form here, but I wrote the dx after there to make a point, but I really didn't need to write it here, but down here I did. But anyway, so now, let's see. Yeah, so now let's look at this, and then you see that if you're supposed to have 3x squared, but you only have x squared, what you can do is you could think of it as, well, I can put a 3 there, but I have to actually divide by 3 also, or otherwise the problem has changed. So then 3 over 3 is 1, so I have the same problem as what I started with. But then I can move this 1/3 out in front of the integral, and then I'm left with this. And then this part right here is g prime of x dx. All right, so that's what I'm looking at here. So think about it like this, all right? So yeah, so you could think of this as the, okay, good. So you could think of this even as 1/3 dy over here if you want it to. All right. So I just want to make sure that you make sure that, again, every symbol in the original problem is accounted for. So if you need to add the 1/3 to make it have the correct derivative, then you need to add the 1/3 in there. So for this particular problem here, secant of 2x times tangent of 2x dx, I have the u is equal to the inside function, 2x, and that means that the outside function would be the, so that would be the g of x, right, or the u, it doesn't matter which letter I use. Then that would mean the outside function, or the f of x, would be secant of x times tangent of x. All right, so now I just need to figure out what g prime of x is. So g prime of x is the derivative of 2x, which is 2. And so then if you look at what is going on here, all right, you have integral of f of g of x, but this is similar to what happened with the 1/3. Do you see how this is just dx? But if I rewrite this in differential form, it is well, it's dy is equal to 2 dx, right? So I need to actually have a 1/2 to get rid of this 2 that we had here. So this would be times 1/2 g prime of x dx. So just how I had the 3x squared here, I needed to put 1/3. Since I had a 2 here, I needed to put a half. All right, so that's essentially what is going on here. And so there you go. That would be the correct answer here. And again, if I wanted to write this in u format, I could write it as, where is it? Secant of u times tangent of u times 1/2 du. All right, so we'll work with the u format more often than with the x's. All right, again, if you have any questions, feel free to ask. But now we are going to, now that we've seen a few examples of how we're going to set these up, actually work on integrating these here. So the first one is actually the same example A that we had before. All right, so if you looked at this, it was u was 2x squared plus 1, and then it was du was 4x dx. So this integral was rewritten as integral of u to the third du. Now I am going to integrate this just by the methods that we had in the last videos. So now this would be, remember the general rule here would be, now I actually just want to make sure that you're very clear on the fact that, again, this is going to be the reverse of finding the derivative. So what I need to do is actually add 1 to the exponent. So that will be u to the 3 plus 1. And then divide by the new exponent, which is 3 plus 1. And then this will be plus c. All right, so this is, well, that's u to the 4 over 4 plus c. And I usually like to write that as 1/4 u to the 4th plus c, in case there's any fractions that will make it difficult for me at the end. So the first thing that I want to remind you about, again, is just don't forget the plus c at the end for indefinite integrals. All right, don't forget plus c for indefinite integrals. And then the other thing is, don't forget to substitute what u was back in at the end. So u was 2x squared plus 1. So this will be 1/4 times 2x squared plus 1 to the 4th plus c. And that will be my final answer. And you don't need to multiply any of this out. You just need to leave it like that, and that would be okay. All right, so hopefully everyone is okay with that. And then the next one here is actually the same as problem B. So problem B, this was u was the x to the 3rd plus 1, and then I said du was 3x squared dx. So remember, I had to have the 1/3 here. So it's 1/3 du was equal to x squared. And this became the, well, did I write that one with the u? Yes. So the 1/3 integral of square root of u du. All right. So now what is going to be the easiest way to find the antiderivative is just to go ahead and rewrite the square root of u as u to the 1/2 power, and then use the power rule that we just used on the last problem. So that will be 1/3 times u to the 1/2 plus 1 over 1/2 plus 1 plus c. So just like before, remember the rule is the integral of, say, u to the n du is u to the n plus 1 over n plus 1 plus c. All right, so I just need to add the 1 to the exponent and then divide by the new exponent. And so if I go ahead and I do that, then 1/2 plus 1 is actually 3/2. So then what I have here is 1/3 times u to the 3/2 over 3/2 plus c. But then if I am dividing by 3/2, that's the same as multiplying by the reciprocal. So that would be like multiplying by 2/3. And then I can see that what I really have here then is going to be, what is this? What is this going to be? This is going to be, oh, yeah, this is actually, believe it or not, this is actually very, very strange that this is the next one here. But anyway, 2/9 u to the 3/2 plus c. And then I can substitute what the u was back in. So I have 2/9 times, what will this be? X to the third plus 1 to the 3/2 power plus c. And that is the final result here. All right, so that is the final result here. So that is, I think, the, well, I think that is the end of that one here. I don't actually, for the sake of being too repetitive, I don't actually think that well, I wasn't going to do the next one, but I feel like it, it, I feel like it's one of those things where I feel like you can do this, but here, okay, so let's just go ahead and do this just so that you can see what would happen here. So if you let u be the inside function here of what is, usually you're looking for something to be raised to some other power or like a trig function of another function. All right, so u would be 1 plus x to the fourth. Then the differential is du is, well, oh, okay, so du is 4x to the third dx. And then you don't see a 4 in the original integrand. So what I'm going to do is actually divide by 4 to get 1/4 du is x to the third dx. Then I just do the substitutions. So this right here was u, and this right here is x to the third dx. So what I have here then is going to be the integral of, all right, now I'm going to watch this, right? This is 1 over 1 plus x to the fourth squared times x to the third dx, so that I can rewrite this as just 1 over u to the second power, because u was 1 plus x to the fourth, and then x to the third dx is the 1/4 du. And then I'll bring the 1/4 in front, just like I brought the 1/3 in front in the last problem. And I have integral of 1 over u squared du. But then, remember how I rewrote the square root of u as u to the 1/2? I'm going to rewrite this as u to the -2, so that all I have to do is add 1 to the exponent and then divide by the new exponent to get what the antiderivative is. So then I have, well, if I simplify this, 1/4, and u to the -2 plus 1 is u to the -1, and then -1 is what we divide by also, plus c. So 1/4 times a -1, or 1/4 divided by -1 is -1/4 u to the -1 plus c. But u to negative 1 is 1 over u. And then I could rewrite this as negative 1 over 4u plus c. And then finally, I could wrap it all up by substituting the u back in here. So I have negative 1 over 4, 1 plus x to the 4th plus c. All right, what a time to be alive. So hopefully that all makes sense, but I wanted to point out to you that the general procedure is exactly the same as what we've been talking about. So just try to remember that. Now, I think that what I will do is let you try this one on your own later, but my hint would be to you that you use u as x squared minus 8x plus 1. All right, so just try. Actually, you know what? This one is a little bit trickier now that I think about it, but I feel like you could. I feel like if I say too much, I probably will have ruined it, but I think that if you factor out the 2 and then divide by the 2, that you can see that this could be rewritten as integral of 1 over the square root of u times 1/2 du, or 1/2 integral of, and 1 over square root of u is u to negative 1/2 power, and then just go ahead and add the 1 to the exponent and divide by the new exponent plus c, just like before. So you have 1/2 u to the 1/2 over 1/2 plus c. And then 1/2 divided by a half is actually, well, I think that you can figure out what is going on here. That's just going to be the 1. So this is just the, what is it? Oh, u to the 1/2 plus c, or square root of u plus c. And if you substitute in the u, it's square root of x squared minus 8x plus 1 plus c. All right, so there you go. I feel like the hardest part is sometimes identifying the u, and then just not making any mistakes when you are going through any of the work. All right, so just try to make sure that you get all of these right and not make any mistakes. All right, so now let's go to another one here. So this is like one that we had before, problem C before. So remember the 2x was the u, so u was 2x and du was 2 dx, so 1/2 du was equal to dx. So this integrand became integral of secant of u times tangent of u times 1/2 du, and then I bring the 1/2 in front, so 1/2 integral of secant of u times tangent of u du. And then this is one of those integrals that is a trigonometric integral that you probably should try to memorize. All right, so if you sort of remember, if we found the derivative with respect to x of the secant squared, or actually, yeah, secant squared x, or actually, which one do I actually want to tell you about first? Because I'm feeling like that's one that I probably don't want to tell you about first, because it's not relative to what we actually want to hear about. So why don't we just go with this one instead? So where's my whiteout here? All right, so the derivative with respect to x of, say, the secant of x, then, not secant squared, so secant of x would be, well, that would be secant of x tangent of x. So that means that, well, these are antiderivatives of each other. All right, so that means that this integral is 1/2 secant of u plus c, and then you substitute in the u, which was 2x, so this is 1/2 secant of 2x plus c. There you go. All right, that is the indefinite integral here. All right, so let's try another one here. So we have integral of sine of x over cosine cubed x dx. So another way to rewrite this is integral of sine of x over cosine of x to the third power. So the cosine of x is to the third power, not the x. All right, so that means that the u should be the inside function. So the u is the cosine of x, and so du will be, all right, du will be the negative sine of x dx. So now, then, what you need to do is rewrite this all in terms of u, but you see here, this is sine of x dx, so I need to actually divide by -1 to get negative du is actually sine of x dx. This is sort of like how I divide it by 3 before and got the 1/3, or divide it by 2 and got a 1/2. Here I just need to divide by -1. So now, this is integral of 1 over, now cosine of x was u, so I have u to the third times negative du, and then bring the negative in front, so minus integral of 1 over u to the third du, but I'll rewrite that as u to the -3 du. And now I can just go ahead and use the power rule for integrals. So I have negative u to the -3 plus 1 over -3 plus 1 plus c, but -3 plus 1 is -2, so I have negative u to the -2 over -2 plus c. But again, I will just write that as the negatives, -1, right, over -2, 1/2, and u to the -2 plus c, or I can write that as 1/2 times 1 over u squared plus c, or just 1 over 2u squared plus c. And then the u was actually cosine of x, so I have 1 over 2, then cosine of x squared, or cosine squared x plus c. All right, what a time to be alive. So I hope that you enjoyed that example here. So now let's have one last one, and then I will introduce a different type of integral rule that you haven't had yet. So here, again, the u needs to be what's under the square root. So u is x plus 1, and du is dx. So this one is a little bit trickier, right? Because I know that I have under the square root u, and I have the dx is equal to du, but what is the x here equal to? All right, that is the issue that I haven't had to deal with before, is what is this x right here equal to? Well, I can see that u is equal to x plus 1, so u minus 1 is equal to x. So now this will be u minus 1 is what gets substituted in for that x. Right? So if you have any questions about that, please feel free to ask. But remember, I said that every x and every constant has to be accounted for. So I am accounting for this x by changing that to u minus 1. All right, now, remember, this was all in terms of x. This is all in terms of u. So I know that I've done this correctly. Now, I will rewrite the square root of u as u to the 1/2 power, just like I've rewritten the square roots before, and then distribute the u to the 1/2 power. So it's integral of u to the 1/2 power times u to the 1 power. 1/2 plus 1 is 3/2, then minus u to the 1/2 power du. And then I can split this up into two separate integrals or just use the linearity properties of the integrals to compute this. So let's just use the linearity property. So u to the 3/2, and remember add 1 all over the new exponent of 3/2 plus 1, minus u to the 1/2, add 1 over the new exponent of 1/2 plus 1, plus c. And then 3/2 plus 1 is 5/2. So u to the 5/2 over 5/2 minus u to the 3/2 over 3/2 plus c. And then finally, I multiply by the reciprocal. So the reciprocal of 5/2 is 2/5. So 2/5 u to the 5/2 minus 2/3 u to the 3/2 plus c. And then you can substitute in the x plus 1 if you would like to. Actually, you should, but I think I may have ran out of room for this, but here, let me see. Maybe there's room for this. Who knows? Oh, bah humbug. All right. So here, just let me get another piece of paper here. Actually, you know what? I'll just write it. I'll keep on writing at the top of the next page so that we can continue on without a lot of extra hassle here. So 2/5 times x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. All right, so again, I don't think that the procedure is too difficult as long as you make sure that every x and every dx and every constant is accounted for when you make the substitution. All right, so if there's any questions, please let me know. But I'm going to move this up. I can come back to it if anyone would like me to. Just let me know. But I am moving this up because the next one is actually a new definition that I really just would say add to your list of things to memorize for the rest of your life. All right, so if you need more things to memorize, here you go. So you should memorize that the integral of the what plus? Oh, yes, okay, so what was that, Nuzrat, plus? So adding this to the list of things to memorize forever. So the integral of 1 over x dx is natural log of the absolute value of x plus c. So memorize, and then also memorize the integral of e to the x dx is equal to e to the x plus c. So memorize that one else as well. So, oh, well, okay. So, well, no, sir, that's good. You're teaching adding and subtracting to your daughter. That's nice. I think that's always a good thing. Start teaching math at an early age. All right. So now I can see here that these are sort of what you would expect because the derivative with respect to x, if you recall, if the natural log of x was 1 over x, and the derivative with respect to x of e to the x was e to the x. So this is exactly what you would expect, all right? So remember that these are the derivatives and these are the integrals to memorize for the logarithmic and exponential functions. All right, so what happens when you have 1 over x minus 5 instead of 1 over x? Well, you just let the u be x minus 5. And so in these types of problems, you should usually let u be the denominator. All right, so keep that in mind as well. So then du is equal to dx. So this integral becomes 1 over u du, but I can apply the rule here to get natural log of the absolute value of u plus c, but then substitute the u back in, so it's natural log of the absolute value of x minus 5 plus c. And I will be very cautious, or in, well, I don't even know if it's a caution as much as it is like just a warning here, I guess, that I remind you to make sure that these are absolute values, all right, because that's part of the definition here, is that this needs to be the absolute value, because remember the domain of the natural log, right? The domain of natural log of x is 0 to infinity. So we want to make sure that whatever this value we're taking the natural log of is a positive value. All right, so just remember that as well. All right, so let's try another one here. So we have 1 over 4 minus 3x. So what I'm going to do is, again, let the denominator be u. So u is 4 minus 3x, and du is negative 3 dx. And I'll divide by the negative 3. So negative 1/3 du is equal to dx. So this integral becomes 1 over u times a negative 1/3 du. So I can bring the negative 1/3 out in front to get negative 1/3 integral of 1 over u du. But this integral is actually, well, the same one I just did up here. So it's natural log of the absolute value of u plus c. So, oh, okay. So yes, okay. So let me go back to, yeah, how do I know that I use this formula and not the power rule formula? Okay, that's a good question. So now the other thing here is that you notice that I'm just adding the constant to the end. That's okay to do that also. All right, like you don't have to actually put this in parentheses and then have negative 1/3 natural log of absolute value of u minus 1/3 of c, right? You don't have to actually do that either, because this, since c is a constant, then you could just actually say that k is negative 1/3 c, and then use some other letter like k to represent what that number is instead of c. But you do need to substitute in the u here, so it's negative 1/3 natural log of the absolute value of 4 minus 3x plus k, or c, or whatever constant letter that you want to use. But let's say that you had the integral of 1 over x dx, and then you wrote that as x to the negative 1 dx, and then you tried to use the power rule and add 1 and divide by the new exponent, then you would get x to the 0 over 0, and you can't divide by 0. So since you can't divide by 0, you know that that cannot be the correct antiderivative, all right? So that's why we need a separate antiderivative for this case here, because the power rule doesn't work because you can't divide by 0. So you cannot divide by 0. So if you actually tried to use the power rule, you wouldn't be able to, because you can't divide by 0. So now let's try another one here. So we have 2x over x squared plus 1. So here we have a fraction, and we don't have, say, one function inside of another function, but we have a 2x over x squared plus 1. So if we let u be the denominator again, x squared plus 1, then du could be the, all right, so du could be 2x dx. So there's 2x dx already in the integrand, so this is the integral of 1 over u times du, and we've had the same integral before, right? This is going to be, well, natural log of the absolute value of u plus c, and we substitute the u back in, so we have natural log of the absolute value of x squared plus 1 plus c. What a time to be alive. All right, so now here is a very tricky one in a way, because if you look at this, if you tried to let and actually, believe it or not, I guess this is one of those places where this would be, in my opinion, a sort of strange thing to do. All right, but I guess you, now that I think about it, you could do it this way. Like if you let the denominator be x plus 5, and then du is dx, then do you see that this is something where you have the 1 over u du, but then you still have all of this up here, and so you have to do this like the other problems that we had before, where it was u minus 5 is equal to x. So then you would have u minus 5 to the third minus 6 times u minus 5 minus 20, all right? And then it's all in terms of u, and then if you went ahead and you multiplied this out, all right, so let's go ahead and do this just so that, well, and by the way, I will tell you that this is not actually the most efficient way of doing this by any means, but I will go ahead and show you this since I happen to already start it this way. All right, so um oh boy, what is this? Okay, so yeah, so 1 over u, and then u minus 5 to the third is actually u to the third minus 15u squared plus 75u minus 125. Then I'll distribute the u here to get minus 6u, and that will be, what will that be? All right, negative 6 times negative 5, so plus 30, then minus 20, and then du. And then if I simplify, I have 1 over u times u to the third. Then we have minus 15u squared. And then we have a, oh boy, what a time to be alive, right? So we have 75u minus 6u. So that will be a, what is that? That's a 69u, right? And then we have negative 125 plus 30 minus 20. So that will be negative 115 du. And then what I will do is I will just go ahead and distribute this, distribute this, distribute this, distribute this. So I have integral of u to the third over u minus 15u squared over u plus 69u over u. And then, well, this is actually pretty extreme if you ask me here. So, but that's just my opinion on this. If I go ahead and I keep on distributing here. Oh boy, what a time to be alive, right? Minus 115 over u du. All right, so now what do we have here, well, we have, oh boy, well, let me go ahead. I'm telling you, this is one of those cases where you actually want to make sure that you don't make any arithmetic error at all, or there might be some serious serious issues here, right? So just try not to make any arithmetic errors here. So I'm actually going to double check my arithmetic whenever I do this. So let me double check my arithmetic just to make sure that there's not going to be any problem here at all, because I feel like there possibly could be a problem, but I guess there's not. So now, uh, what do we have here? So we have integral of, well, this will be, oh boy, u squared minus 15u, then that will be plus 69 minus 115 over u du, and then go ahead and just simplify all of these. So let's find the antiderivative. So this will be u to the 2 plus 1 over 2 plus 1, and then minus, all right, 15 to the u plus, well, 1 plus 1 over 1 plus 1 plus 69 u minus 115, and remember that negative 115 over u is actually negative 115 times 1 over u. So this is actually minus 115 times the natural log of the absolute value of u, then plus c. So now I have, when I simplify this, I have u to the third over 3 minus 15u squared over 2 plus 69u minus 115 natural log of the absolute value of u plus c. And then I can substitute in the u, which was x plus 5. So then I am left with the, oh boy, x plus 5 to the third over 3 minus 15 times x plus 5 squared over 2, then plus 69 x plus 5 minus 115 natural log of the absolute value of x plus 5 plus c. All right, so now the other thing that I want to point out to you then would be this. All right, so let me go ahead and show you another method of this, because honestly, this is what I just did is sort of tedious, and also what I'm about to show you actually could be useful if you're solving problems other than this one. All right, so if I have integral of x to the third minus 6x minus 20 over x plus 5 dx, then if the now, by the way, just so that you're absolutely aware of this, like if the degree of the, right, if the degree of the denominator, all right, denominator is actually less than or equal to the degree of the numerator. So we have talked about this in the past when we were finding the different asymptotes, I think. But then you can use long division, or we can use synthetic division to divide these, and then we find the antiderivative. All right, so let's go ahead and we'll divide these. So if I go ahead and I divide these here, so let's do that. All right, so what do we have? We have x plus 5 goes into x to the third plus 0x squared minus 6x minus 20. So don't forget to put the 0x squared here. And then I am going to actually opt for the synthetic division. So I have to use c is -5, so -5. And then the coefficients of the numerator, the p of x, that will be 1, 0, -6, -20. Then I'll bring down the 1. -5 times 1 is -5. I'll add those together. So 0 plus -5 is -5. And then I have -5 times -5, that's 25. -6 plus 25 is 19. The -5 times 19 is going to be, what is that going to be? That will be negative, uh, what is it? 50, negative 95. So if I add these together, I have negative 115. All right, so now what do I do after this? I go ahead and I rewrite the x to the third minus 6x minus 20 over x plus 5 as, all right, so this will be x squared minus 5x plus 19 minus 115 over the this is the remainder. All right, so the remainder out of x plus 5. So this integral will be equal to this integral dx, all right, the integral of this dx. So now I just find each of these antiderivatives. So the antiderivative of x squared is x to the 2 plus 1 over 2 plus 1. Then the antiderivative of the 5x is x to the 1 plus 1 over 1 plus 1. And the antiderivative of the 19 is 19x, and then the antiderivative of the negative 115 over x plus 5 is still minus 115 natural log of x plus 5 in absolute value plus c. So then if I simplify, I have x to the 2 plus 1, that's x to the third, so x to the third over 3 minus 5x squared over 2 plus 19x minus 115 natural log of the absolute value of x plus 5 plus c. Now this is the same answer, right? The same answer as what I got before, and what I had before was actually the x plus 5 to the third over 3 minus 15 x plus 5 squared over 2 plus 69 x plus 5 minus 115 natural log of the absolute value of x plus 5 plus c. So these are the same answer, but do you see that this was actually, in my opinion, this was a little bit quicker because I didn't have to multiply out the u minus 5 times u minus 5 times u minus 5 and then distribute this and then find all of these antiderivatives. All I had to do was long division, and these might not look the same, but you see that this is actually x over 3, and that's x plus 5 cubed over 3, right? So if you multiply these all out and actually recombine the like terms, you would end up with this. But you don't have to do that except for Howard, all right? So no one else has to multiply this out and show that these are the same except for Howard. So hopefully there are not too many things that you think could go wrong here, but I do think that it is interesting to be able to look at this type of problem in more than one way. So now let's look back at the problem M. So that one was, let me get another piece of paper since I I wasn't actually going to show both ways, but then I really feel like at the last minute I decided it might be helpful for you to see that there is more than one way to evaluate this particular integral, but the results will look maybe slightly different, but you can get them to look the same if you multiply uh, these all out over here. All right, so now problem M was the integral of sine of theta over 1 minus cosine of theta d theta. So when I have a problem like this, again, I might go ahead and I might let the denominator be equal to u. So u is 1 minus cosine of theta. Then du is going to be negative, all right, negative sine of theta d theta. So that will be du is sine of theta d theta. So now I see that u is 1 minus cosine of theta, and sine of theta d theta is du. So this is the integral of 1 over u du, and I've seen that integral over and over again here. So that's the natural log of the absolute value of u plus c, and then u was 1 minus cosine of theta. So there is my final result. So I really hope that you enjoyed that. So now let's go ahead and look at a couple of more examples here. So I feel like I can't say too much else here, but I I do hope that again that you're enjoying this here. Whoops. All right, my pages just fell on the floor over here, and I'm struggling to figure out what the next page number is supposed to be. Oh well, I hope that you're all doing okay over there. So it should be. Is it? Does anyone know the next page number? Oh, all right. Thank you, Howard. All right. Oh, here it is, 243. I I can't believe this. All right, so now we have in the integral of e to the power of 1 minus 3x dx. So remember that one of the antiderivatives I mentioned to memorize is the integral of e to the x dx. So if I have e to the power of a variable x, then I will try to always let the exponent be u. All right, so I'm going to let u be 1 minus 3x, and in this case, du is going to be negative 3 dx, and then I'll divide by negative 3, which will give me negative 1/3 du is dx, and I can go ahead then and just do the substitutions just like before. So this will be e to the u times negative 1/3 du, and bring out the negative 1/3 in front of the integral. So I have negative 1/3 integral of e to the u du, and the integral of e to the u is e to the u plus c, so negative 1/3 e to the u plus c, and u was 1 minus 3x, so I have negative 1/3 e to the 1 minus 3x plus c. So again, the integral of e to the x dx is e to the x plus c. So now, look at the next one. I think that this one is a little bit trickier because it is one where I see that e isn't to an exponent other than x. However, I see that we have an expression inside of another expression. So I have probably going to have a situation here where I let u be the inside function. So whatever is being squared here, so that's e to the x plus 1, then du is e to the x dx. But I see that e to the x dx is already in the problem, so this actually just becomes integral of e to the x dx was du. So that means what I have here is, oh, yeah, so I have u to the second power du, and then I just use the power rule, so I add 1, so u to the 2 plus 1 over 2 plus 1 plus c, or u to the third over 3 plus c, and then I just substitute the u back in, so I have e to the x plus 1 to the third over 3 plus c. All right, what a time to be alive. So now, I hope that in the next one you see that e does have an exponent other than x. It has an exponent of 2x. So I'm going to try to let u be 2x, and then you could let the du be the 2dx. Now, is that actually a good way to do that here? Well, I'm not so sure about that, because then all you really have here, all right, all you really have here is e to the u over 1 plus e to the u, and then you have 1 half du is equal to dx. So I have 1 half du here, and then I still have e's in the problem here, but there's not an issue with that. It's just now I have the 1 half and the integral of e to u over 1 plus e to u du. And I can look at this and say, well, all right, remember all of those problems where I had the numerator and the denominator, right? I might actually let the denominator be something that I substitute, but I can't use the letter u again because I already had the letter u in the problem. So I'm going to let's just let let's let n for Nuzret be 1 plus e to the u. So that means dn is e to the u du. And so then if I go ahead and I simplify this, I have the 1 half integral of, all right, so e to the u du was dn, so I have 1 over n dn, but then look at this, that is a natural log integral. So this is 1 half natural log of the absolute value of n plus c, and so then n was 1 plus e to the u, so I have 1 half natural log of 1 plus e to the u plus c, and then u was 2x, so then I have, 1 half natural log of the absolute value of 1 plus e to the 2x plus c. So that is my final result. Now, oh, excuse me, it's a little bit dusty here in the basement right now, so let me get another piece of paper here to show you something else here, because something else that I personally find interesting would be this. Oh, oh, all right, there we go. So, let's see. Yeah, so now, let me write down the problem again. Integral of e to 2x over 1 plus e to 2x dx. And then, what happens if instead of letting u be the 2x and thinking of it as an exponential integral like I did originally, I go ahead and I look at it as a logarithmic integral, and I go straight to letting u be 1 plus e to 2x, and then du would be 2e to 2x dx, because I need to use the chain rule here. So then I multiply by a half or divide by 2 to get 1/2 du is e to 2x dx. And so then this integral becomes, all right, so e to the 2x dx is 1/2 du. So it's 1 over u times a half du. I'll pull the 1/2 in front, so 1/2 integral of 1 over u du. But this integral is a natural log integral, so I have 1/2 natural log of the absolute value of u plus c, or u was 1 plus e to the 2x, so it's natural log of the absolute value of 1 plus e to 2x plus c. So again, there are two ways to do this, thinking of it originally as u being 2x, the exponent of e to the x, or u being 1 plus e to the 2x, which is the denominator here. All right, so then the only difference is that thinking of it this way only require using one substitution and not two substitutions. So that made it perhaps a little bit easier. All right, so again, if there's any questions, please let me know, but I'm going to try to go on to problem Q now. So Q is the integral of x e to the 2x squared dx. So then again, I usually want to let u be the exponent of the exponential function here. So u will be 2x squared dx, or 2x squared, and then du will be 4x dx. All right, so now I kind of want to wipe that out now, but I actually don't even know where my whiteout is, so that's okay. Oh, you know what? Okay, so now what do we have here? We have, when I divide by the 4 or multiply by a fourth, I have, oh boy, what a time to be alive, right? I have 1/4 du is x dx. So this ends up becoming integral of, here's x dx, so e to the u times 1/4 du. I'll bring the 1/4 in front to get 1/4 integral of e to u du. And the exponential integral, that will just end up giving us 1/4 e to u plus c. And then I can go ahead and substitute u back in to get 1/4 e to the 2x squared plus c. All right, what a time to be alive. So again, just make sure that you are very careful with what you pick to be u, and I'm certain that you can do these just perfectly. So that is it for this section here on the method of substitution, or the u-substitution.